Hi, welcome to another lecture about topology. We are going to talk about the characteristic property of subspace topology. As we proceed into the new spaces that are obtained from those spaces that we already knew about, we see that each of them satisfy a characteristic property, and this characteristic property is unique to them, and no other topology can satisfy this. So if we see some topology is satisfying this property, we say that it must be that unique topology. Okay, there are no other topologies that satisfy this. Before that, we just want to see the definition of what an inclusion map is. And I want you to think about that if an inclusion map is continuous. So an inclusion map looks like an ID map. It's just that the inclusion map is between a set and a subset. Actually, it's between a subset and a set. Okay, if S is a subset of X and this thing is X, then these will map anything that is here. Okay, let me copy that. This thing will include your space to the bigger space. Okay, this is just the definition of what an inclusion map is. Now, we reach the characteristic property of subspace topology. So let's suppose that X is a topological space and S is a subspace. Then a map between Y and S is continuous if and only if the composition of the inclusion map and F is continuous. And there is a diagram right here to show the visuals. So if F is continuous, then the inclusion map and the F, their composition should be continuous. And if the composition is continuous, then so is F. Let's prove that. First, let's suppose that F is continuous. When we say that F is continuous, then if you take an open set in your image, which here is S, so if U is an open set in S, then the inverse of U, which is in Y, will be open. And since S is the subspace topology, then U must be equal to S intersected by V, which V is a subspace of X, which V is an open subset of X. So now I want to prove that this thing is continuous. So let's just take an open set in X. Okay, my open set is going to be V. And if I take an open set in X and let's do the inverse image of that. And by abstract algebra, we know that the inverse of composition will look like this. Now I have to prove that this is an open set. This thing right here will become S intersected by V, and F inverse of S intersected by V by hypothesis is an open set. Now I have proved that F is continuous, so is the composition. Now I have to assume that the composition is continuous, then F is also continuous. So if the composition is continuous, then if I take, let's see where the space is. So if I take an open set in X, then the inverse image of the composition of U should be an open set in Y. Now I want to take an open set in F to prove this, to prove the assertion. If I take an open set in S, okay, so an open set in S would look like U intersected by S, or V intersected by S, doesn't matter. So this thing is open, and I'm going to prove that the inverse of U intersected by S is open. And again, this was an inverse. This thing will become F inverse of inclusion map inverse of U. And again, this will become U intersected by S. And since this is open, that's exactly what we have here. So this is open. Now, there is a corollary to this. I asked you to prove that an inclusion map is continuous, but there is an easy way. Okay, let's just copy what we have here. Now, to prove that an inclusion map is continuous, I only have to do one thing, actually two things. Just need to replace f with the identity function. So here is identity, and replace y with s. And now, by the characteristic property of subspace topology, this thing is continuous, okay? Because the ID map is continuous, so should be this, and this is just equal to the inclusion map. There is another corollary which is really useful, and it talks about the restricting the domain or the codomain and expanding the codomain. So just look that there is no expanding in the domain. But if you restrict the domain, then it does not change the continuity. And why is that true? Because we just proved that the inclusion map is continuous. And if f is continuous, then the composition of f composed by the inclusion map, this thing will be continuous. So you can restrict the domain. For the codomain, restricting and expanding works like what we just proved above. As you can see right here, this is the inclusion map composed by f. So if you just want to restrict or expand the codomain, you have just to change s to do this. That's the characteristic property of subspace topology. I hope you have enjoyed this video. Please like and comment. I would really appreciate it, and it would really help me.